Welcome to this Concept Explainer brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are undertaking a deep dive into a really important topic from Unit 2, electrostatic potential and capacitance. We'll be talking about the energy stored in a capacitor. And our mission, as always, is to make this so simple you'll understand it perfectly and score maximum marks.
I'm looking forward to this. You know, when we think of storing energy, the first thing that comes to mind is a battery. So why do we need this whole separate device, a capacitor, just for energy storage? What's the real difference?
That is the perfect question to start with, and it leads us straight to our curiosity hook. You're right, a battery stores energy.
Yeah.
But think about your camera flash.
Okay.
Why can't we just run that flash off a normal battery?
Right.
What allows that small capacitor to unleash such an instant, massive burst of light?
I suppose it's about the speed, isn't it? Batteries give steady power, but they're slow. The flash is so quick.
Exactly. It's all about the rate of delivery, the difference between total energy and power. The capacitor is a sprinter. Take a more extreme example, a defibrillator in a hospital.
Right, the device they use to give a shock to restart a heart.
Yes, it delivers a huge jolt of energy, hundreds of joules, in just a few milliseconds. A battery just can't push energy out that fast. That incredibly high instant power that's entirely thanks to the energy stored in and then dumped by the capacitor.
Okay, so capacitors are for storing and then releasing energy extremely fast. But how does the energy get in there in the first place, and where? Where does it actually stay?
Right, so let's unpack the core idea. The main thing to understand is that charging a capacitor requires external work. And crucially, this work is it's nonlinear. It's not like just pouring water into a glass.
What do you mean nonlinear?
Well, a capacitor has two conducting plates, right? To charge it, you're essentially moving charge from one plate to the other. When you start, the plates are neutral. So moving that first little bit of charge is very easy. There's no opposition.
Makes sense. No existing electric field to push back.
Precisely. But as you move more charge, a potential difference starts to build up between the plates. An electrical pressure. Now, to move the next bit of charge, you have to fight against the repulsion from the charges already there.
So the effort required keeps increasing. It gets harder and harder the more charge you add.
Exactly. And all that work you do, fighting this constantly increasing opposition, that's what gets stored. It's stored as electrostatic potential energy.
This increasing effort.
Right.
Is there a good way to visualize this?
Yes, there's a perfect analogy. Think of it like compressing a spring.
Okay.
The first millimeter of compression is easy, almost no force needed. But as you squeeze it more and more, the force you need to apply increases rapidly, doesn't it?
Yes, of course. And the energy stored in the spring is proportional to the square of the compression, x squared.
Exactly the same logic here. In the capacitor, the total work done ends up being proportional to the square of the final potential, v squared. This nonlinear effort is why the formula isn't simply Q times V.
That analogy helps a lot, so the work gets stored. But my earlier question, where is this energy physically located?
This is a beautiful concept. So the plates hold the charge, yes, but the actual energy resides in the tension in the electric field between the plates. You must picture the electric field like a stretched slingshot.
A stretched slingshot. I like that.
The charges on the plates create the tension, but the energy is stored in the stretch. When you discharge the capacitor, you release that tension. The field collapses and converts its stored energy into that burst of power.
So the key phrase to remember would be something like, field is fuel.
Field is fuel. Perfect. The energy belongs to the entire system, the field, not just one plate.
That clarifies the physical picture so well. Okay, so now that we have the concept, how does NSERT formally define this for the exams?
Good. We need to be precise for the board exams. Could you read the core idea about electrostatic work from our source material?
Yes. It says, since electrostatic force is conservative, this work is stored in the form of potential energy of the system. Thus, the potential energy of a system of two charges Q1 and Q2 is U equals 1 upon 4 pi epsilon naught Q1 Q2 upon R12.
Excellent. The key word there is conservative. It means the work we do is fully recoverable as potential energy. Now let's use that principle to derive the specific formula for capacitor.
This is the part that can be a bit tricky. How do we get from that general formula to the one for the capacitor?
It's a few logical steps. The main thing to remember is that the voltage isn't constant while charging. So we have to use calculus. We have to sum up the work done in tiny little steps. So imagine we are at some intermediate point in the charging process. Let's say a charge Q prime is already on the plates.
Okay.
At that instant, the potential difference, let's call it V prime, is simply Q prime divided by C.
Right, from the definition C equals Q by V.
Exactly. Now, to move the next tiny bit of charge, dq prime, we have to do a small amount of work, dw. And work is just potential times charge.
So dw would be v prime times dq prime.
Perfect. Now we just substitute our expression for v prime into that equation. We get dw equals
q prime by c times dq prime.
Yes. And that's the work for just one tiny step. To get the total energy U, we have to add up all these tiny bits of work.
So we integrate.
We integrate. We sum it all up. From the starting point of zero charge all the way to the final charge, Q. And when you perform that integration of Q prime by C from 0 to Q, the result is W equals Q squared divided by 2C.
And that's it. That work done is the stored potential energy. Ooh. The integration naturally gives us that factor of 2 in the denominator.
Precisely. This is the most fundamental form. U equals Q squared over 2C. From this, using Q equals CV, we can get the other two forms.
Which are 1 by 2 CV squared and 1 by 2 QV.
Correct. And all three represent the exact same physical quantity. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROFSAM.com. Now let's make this concrete with a quick worked example. It's from the insert material itself. Suppose we have a 900 picofarad capacitor and it's charged by a 100-volt battery. We just need to find the energy stored.
Okay, so we have C and we have V. The easiest formula to use here would be U equals 1 by 2 CV squared.
Absolutely. First step is always units. 900 picofarads is 900 into 10 to the power of minus 12 farads.
And V is 100 volts, so we plug it in. U equals 1/2 times 900 into 10 to the minus 12 times 100 squared.
Right. And 100 squared is 10,000, or 10 to the power of 4.
Okay, so a little bit of calculation. That gives us 4.5 into 10 to the power of minus 6 joules.
Perfect. It's a straightforward calculation once you pick the right formula and get the units correct. Now let's go back to our mental image. Field is fuel. Since the energy is in the volume between the plates, we can define something called energy density.
Energy per unit volume.
Yes. We use the small letter U for it. It tells us how densely the energy is packed into the electric field. And if you derive it for a parallel plate capacitor, something amazing happens. All the capacitor-specific things like area and distance, they cancel out.
Really? So what's left?
They're left with a beautiful general formula. The energy density, U, is equal to 1/2 times epsilon naught times E squared, where E is the electric field strength.
Wow, so the energy density in a space only depends on the strength of the electric field there, nothing else.
Exactly. And this idea is so fundamental. When we study LC oscillations later, you'll see energy sloshing back and forth between the capacitor's electric field and the inductor's magnetic field. And even later, in electromagnetic waves, light itself is just energy traveling because of oscillating E and B fields. This formula is the starting point for all of that.
That really shows how important it is to get this concept right now.
It is. Which brings us to the silent killers, the common mistakes that cost students marks in the final exam. The single biggest mistake, year after year, is students writing the energy formula as U equals Q times V. You just forget the half.
Why does that happen so often? I think it's because in the previous chapter we learned that the potential energy of a charge Q and a potential V is just QV.
That is the exact point of confusion. Students mix up the energy of a single charge placed in a fixed pre-existing potential.
With the energy required to build the entire system of charges from scratch.
You've got it. In the capacitor, the voltage wasn't fixed at V from the beginning. It started at 0 and grew. So the correct logic is to think about the average voltage during the charging process. Since it increases linearly from 0 to V, the average is just
V by 2.
Yes. So the total work is the total charge Q multiplied by the average voltage V by 2, which gives us our formula, 1 by 2 QV. Here's a way to never forget it. Picture the graph of voltage versus charge, V versus Q. Since V equals Q by C, it's a straight line.
Okay, a straight line through the origin.
The work done is the area under that graph. And what shape is that area?
It's a triangle.
A triangle. And the area of a triangle is 1/2 times base times height. 1/2 times Q times V. It's not a rectangle.
That's a fantastic way to remember it. The area is a triangle, so I need the factor of 1/2.
Always. U equals QV is for a fixed potential. U equals 1/2 QV is for building the potential from 0.
Got it. That's a lifesaver.
Okay, let's lock this in with a few memory anchors. For the formula U equals 1 by 2 CV squared, just think of the kinetic energy formula from class 11.
1 by 2 mv squared.
See the similarity. CV squared over 2 has the same structure as mv squared over 2. It just connects the new idea to something you already know very well.
That's a neat trick. It makes it feel familiar.
For the core concept, our phrase is field is fuel. It reminds you where the energy actually is, in the field,
Not on the plate.
not on the plates. And finally, a physical gesture. To remember the nonlinear work, think about stacking bricks.
Stacking bricks.
Yes, the first brick is easy, but to place the 10th brick, you have to lift it much higher. The work increases as the stack. The potential gets higher. It's the same idea.
So the kinetic energy link for the formula, field is fuel for the location, and stacking bricks for the nonlinear work. That's very helpful.
Great. So to conclude this deep dive, let's summarize with 3 essential exam-safe points. First, the potential energy, U, stored in a capacitor, is equal to the total work done by an external source to charge it from 0. Second, the fundamental formula is U equals Q squared over 2C. And remember, this is interchangeable with 1 by 2 CV squared and 1 by 2 QV. Always include the 1 by 2 factor. And third, physically, this energy is stored in the electric field between the plates. The energy per unit volume, or energy density, is given by U equals 1/2 epsilon naught E squared. To get maximum marks in 12th CBSE, physics, chemistry, and maths, visit ProfSam.com.
That is PROF-SAM, right?
Yes, PROFSAM.com. Thank you for joining us for this concept explainer, and we wish you the very best in your studies.